Hi there, welcome to this lecture series on matrix algebra. This is lecture 29, part 2. The topic is symmetric matrices. In this part, we'll continue our discussion on properties of symmetric matrices. Let's now consider the case where the matrix has a repeated eigenvalue, and we'll go through this with an example first. So let's take a matrix A like this, and then we notice that the rows of A are very special in the following sense that if you multiply the first row by 2, you get the second one, and then if you multiply the first row by 3, you get the third row. Therefore, these row vectors are linearly dependent, and you can calculate it if you like that the determinant of A is 0, which means that the determinant of A minus 0 times identity equal to 0, and then 0 is an eigenvalue. And we can find the corresponding eigenvectors by solving the following system, that is, a vector such that A times it equals 0. So we want to solve for this system. And then we can see that basically this is represented by just one equation, that is x1 plus 2x2 plus 3x3 equals 0, because the second and the third are just the same. So we can choose two arbitrary constants. Let's say we pick x2 and x3 to be two arbitrary constants. We call one c2 and call the other one c3. And then you can solve for x1 from that equation. It's just negative 2 x2, which is c2, minus 3 x3, which is c3. Okay, and then we can write out two eigenvectors by making two choices. The first one is make one of the constants 0 and the other 1. So one will be c3 0 and c2 is 1, and then you get this vector, and the other one will be c2 is 0 and c3 is 1, and then you get this vector. So these two eigenvectors are linearly independent. So we see now also lambda equals 0 is a double eigenvalue. So that means the characteristic polynomial P of lambda, which is computed as the determinant of A minus lambda I, if you write that out in a factorized form, this would be one eigenvalue minus lambda, another eigenvalue minus lambda. These are both 0, so we put in 0 here, and the third one, lambda 3 minus lambda. So the question now is how can we find the third eigenvalue, lambda 3? Probably using some smarter properties instead of really working this out. So we can use the property that we have learned, that is, the sum of all the eigenvalues is the trace. What is the trace of A? Well, the trace of A is the sum of the diagonal elements. So here will be 1, 4, 9. So we'll get that. And you add them up, you get 14. And 14 should equal to lambda, the sum of the three eigenvalues, lambda 1, lambda 2, lambda 3, where we already know lambda 1, lambda 2 are 0. So this immediately gives us lambda 3 is 14. And then we can carry out the similar procedure of finding the eigenvectors v3 by solving this system. And let's put out all the components, write it out. That's A minus 14 identity, and that's the vector, equals 0. And then if you solve this and you find that v3 can be 1, 2, and 3. Now let's check if the three eigenvectors are actually perpendicular to each other. So we have three eigenvectors, v1 and v2 and v3. And the eigenvalues is lambda 1 and lambda 2 and lambda 3. So one can easily verify that V1 and V3, they are perpendicular by carrying out the inner product. And in fact, this is already guaranteed by the theorem we had last time. That is, the eigenvectors correspond to two distinct eigenvalues of a symmetric matrix are perpendicular. Okay, and then the same relationship between lambda 2 and lambda 3, they are distinct, and therefore the V2 and the V3 are perpendicular to each other. And however, here, if you check V1 and V2 just as they are now, and you see that they are not perpendicular to each other. So V1 dot V2 would actually equal to -2 times -3, which is 6. So the question now is, how do we get an orthonormal basis W1, W2, W3? So this reminds us of something we learned earlier in this lecture series, and that is the Gram-Smith algorithm that will generate a set of orthogonal or orthonormal, if you wish, vectors. Okay. So let's apply that. Let's compute the W1, which is just a normalized vector of V1. So V1 divided by the norm of V1, and we can work it out, and we get that. And to generate the second vector, let's first generate a vector before we normalize it, and we call that W2 tilde. This is calculated as V2 minus V2 dot V1 times V1. So this is the projection of V2 onto the space spanned by W1. Okay, so we have V2, we have W1, we put it in all the numbers and work out this, and that's what we will get. And then we see that this is a vector that's perpendicular to W1, but it's not a normal vector. So let's normalize it by calculating the norm of it and then divide the vector by it. So we get this vector, which has norm 1. So that's our W2. And now for W3, we already know that the V3 is perpendicular to V1, and then V3 is also perpendicular to V2. And therefore, V3 would also be perpendicular to both W1 and W2. Okay, and you can also easily verify it. There are all the numbers here, W1, W2, and V3. You can easily do a calculation and verify that. So what we need to do is only to normalize it. So we take the V3 divided by the norm of V3, and we get our W3. So working out the numbers, and we'll get that. Finally, we need to say a few words about W2 being an eigenvector for A with the eigenvalue 0. So one way to verify it is to just plug it in and check if this identity holds. A W2 is 0 times W2, which is true. We have all the numbers, you can easily verify that. And another way of thinking this is that W2 is generated by projecting V2 into the span space of V1 orthogonally. So if V1 and V2 are both solutions to the equation A times x equals 0, and then any linear combination of them is also a solution to this homogeneous equation because it's 0 on the right hand side. So W2 is also a solution. Therefore, it also makes this equation hold, and so it's an eigenvector. So let's summarize what we have shown so far. So we have shown that the symmetric matrix A here, this matrix we started with, it admits the following orthonormal basis of eigenvectors. There are these W1, W2, W3 that we constructed. Now we can form this P matrix by collecting these three vectors as its columns, and this will be a 3 by 3 matrix if we fill in the numbers, and that's what we will have. And it's the three vectors are orthogonal to each other, therefore linearly independent, so P is invertible, and the inverse is the transpose, so we can work that out. And then we can work out the calculation that P inverse times A times P, which will be a diagonal matrix, we call it D, where on the diagonal should be the three eigenvalues. So lambda 1, lambda 2, and lambda 3. Here lambda 1 and lambda 2, they are both zeros. Now we look at some more properties of symmetric matrices. So here is a claim. That is, for a real valued m by n matrix A, the following statements are equivalent. Part 1, A is symmetric, and part 2, there exists an orthogonal matrix P such that D equal P inverse A times P is diagonal. Let's look at a little proof. So to show statement 1 implies statement 2, this we have just shown through our calculation and our study so far. So what remains to show is the other way, that is, statement 2 will imply statement 1, this part. So we need to show that assuming statement 2 holds, then A is symmetric, meaning that A transpose equals A. Okay, so let's see what is the assumption in 2. So P is an orthogonal matrix, and therefore the P inverse is the P transpose. And then we can write A, which is P times D times P inverse. And then we can replace the inverse by P transpose. Now let's compute A transpose based on this computation. And our goal is to show that A transpose equal A. Okay, so A transpose is this thing transposed, which is this thing here. So we use the property that the transpose of the product is the product of the transpose, but in reverse order. So we'll take PT transpose and D transpose and P transpose. We write out like that. And then PT transpose is P itself. And D is a diagonal matrix. D transpose is D. And then we have P of transpose. And then this here is the same as that, and which equals A. So therefore we have shown that A transpose is A, and A is symmetric. So statement number 2 implies statement number 1. We now focus our attention on a special type, a class of symmetric matrices, which has applications later on. We will discuss that. So now let A be a real valued matrix, and any size, so m by n. This is not necessarily a square matrix. And then I can make a square matrix out of it, and the matrix size will be m by n. Let's call it B. B is A transpose times A. And then we know that B transpose is B, so B is symmetric. And moreover, B would have real non-negative eigenvalues, okay, and an orthonormal basis of eigenvectors. Now let's see a proof for this. So first we can verify that B is symmetric, because what is B transpose? Well, B is A transpose times A, and I'm transposing that. And then again, using the property, it will be reverse the order and transpose on each. So I'll have A transpose times A transpose transpose. and this is just A, so it's A transpose A, and I got B back. So B is symmetric. Next, we need to show that the eigenvalues are non-negative. Because if B is symmetric, then we already know it has real eigenvalues. This we just learned. Now we need to show that they are non-negative. So in assuming that, then the lambda here must be bigger than 0. Okay, let's do this computation. Let's do the V transpose times B times V. And then V is an eigenvector of B like that. So B times V is lambda V. So I get this. That means I can put lambda to the front because it's a number, and I have V transpose times V. And V transpose times V is just the square of the V norm. So I have lambda times V norm square. So this is one way of computing this quantity. But then the same quantity can also be computed in a different way. We can compute this by using the fact that B is A transpose times A. So we put it in A transpose times A for B here. And now we're going to group the first two product and the last two product, group two of them. So the last two makes AV, and the first two becomes V transpose times A transpose. Then I can put the transpose afterwards and do A times V first. Now I see I have this A times V is a vector now. This vector transpose times itself, which is the square of the norm of this vector. So the same quantity is computed in two different ways, and then these two must equal to each other. So this equals that, and then I have an expression for lambda, which would be AV norm square over the V norm square, and then everything here is positive, so or non-negative, so the whole thing is bigger than or equal to 0. Okay, so let's take an example. We have a matrix A, which is not a square matrix, and then we form the matrix B by computing A transpose times A, which is this times that, and you end up with a 2 by 2 matrix if you work out the detail. And we can compute the characteristic polynomial, the determinant of B minus lambda I, which will be the determinant of this matrix, and which you work out, you get that. And then you can compute the two eigenvalues by the formula, which will be this expression here, and work out what's in the square root. It's 26. Then you know square root of 26 is 5 point something. So one root is about 8 plus 5, the other is about 8 minus 5. But they are both real and they're both positive. Okay, so at least for this little example, we verified the statement of the previous theorem. We have reached the end of this lecture. So the next time we will study something called quadratic form, which rely on this very last theorem that we just covered, and it will take that lots of the properties there and to apply it to something called quadratic form. Okay, so I hope you enjoyed today's lecture, and I'll see you next time.